Hi, we're going to take a look at parametric derivatives, and today we're going to just do a mechanical look at this, but this is going to get deeper and more conceptual later. And why do we need parametric derivatives? Because you recently graphed this still relatively simple parametric curve based off of these two parametric equations, and you got to admit this thing is curvy, which means it has a changing slope at any point. In fact, this thing even has concavity, which would call for a second derivative. So because of that, you get this, a first and second derivative. And it's not going to be laden with excitement because what you basically have to do is just memorize the procedure for finding dy dx or the second derivative in these things. And I'll give you a little bit of background. First of all, on the second derivative, for right now, I'm just going to say ugh. We're just going to have to memorize how to get that done. For the first derivative, though, this is something that in the beginning easily can go into your head. We have dy dx equals dy dt over dx dt. So you're going to do the derivative of y with respect to time and just put it right over the derivative of x with respect to time. And then you're going to have your derivative. But check this out, just for a little informal proof. Here is the derivative, dy dt over dx dt. But of course, if I divide by a fraction, I get to multiply by its reciprocal. And when I do, the dt's cancel and I'm left with the dy dx. So that's just a little nifty way to show you that that derivative is not voodoo, it's the real thing. So anyway, why don't we do one example of each and then call it good enough. So I'm back into the note packet, and this is my set of differential equations. Where is it? Oh, there they are down here. I rewrote them up here, so taking the square root and putting it in exponent of 1/2, which is easier for the power rule. And now if I have to do the dy dx, I'm just going to do the equations, or the y equations derivative over the x equations derivative, and it is literally that easy. So I do the power rule here. This is equation y. That looks like 6t minus 2. This one, x of t, looks like 1t to the negative 1/2. Or I could do some rearranging. I certainly don't have to do some rearranging, but if I felt the need, I could turn this into 1 over the square root of t, and there's definitely other ways that you could go if you felt like doing that. But at this point, we have the formula that will give me the slope of this curve at any time that I care about. This dy dx, by the way, is going to have deeper meaning later. We're going to compare it to some dy dt's, dx dt's, and things like that. Okay, no big deal. Just memorize the procedure. Now the second derivative, that's the one that's just a little bit non-intuitive. So you got to be careful and put a little bit of time into making sure you understand this procedure. So the first thing I'm going to do is just recopy the formula for the second derivative. And it's basically saying take the derivative with respect to time of dy dx, which is the first derivative that you just got. And in the denominator, don't overthink it, just put down a dx dt, which is also something that you already have. So the second derivative is going to be something very, very related to the work that you've done in your first derivative. Kind of makes sense that way. So I know my denominator is going to be dx dt. Well, I've already done that, so I'm just going to recopy that. So there's really no work to do in the denominator of the second derivative. However, the numerator is the derivative with respect to time of dy dx, which means I need to take the derivative with respect to time of this. This is my dy dx, and that doesn't look to be in a very good form. So what I'm going to do is do a different eyeball adjustment and take this and rewrite it. If I take the t to the negative 1/2 and divide it into the 6t, I would get 6t to the 3/2 power. And likewise, if I take this and divide it into there, I would get minus 2t to the 1/2 power. So that's yet another version of my dy dx. And that version is going to make it a heck of a lot easier to take the derivative with respect to time of dy dx. Little power rule action here, that would be 9t to the 1/2 minus t to the negative 1/2, that's a t. And I actually am complete. I could rearrange it again, but why do that unless I need to? So I've now completed a second derivative and a first derivative, and it's all based on me just making sure I memorize those rules. It's as simple as that. The AP test will definitely call upon you to do these derivatives, and they definitely get tedious. We'll also apply these to motion problems later on, and we'll put some deeper conceptual understanding. But for right now, just the rules. See ya.